Good morning to all of you. I welcomes to all in our lecture series on solid state physics. Today we are going to discuss about classical Langevin theory of diamagnetism. In our last class we have been discussed about how a atom as a magnetic dipole or the so-called orbital magnetic moment of an electron. That means when one electron revolving around the nucleus, it is act as a current loop, and due to this current loop we can found the magnetic moment. So if this electron is revolving in this way, that means anticlockwise, then we can found the angular momentum direction in this way towards top side, and its corresponding magnetic moment to the opposite of the angular momentum. Mathematically we have been discussed in our last class, and we also found that mu L, this is in the vector form, we can found that the mu L, the so-called orbital magnetic moment, is opposite to the orbital angular momentum, that is L. Here this side is your L and this side is your mu L. That means simply we have to remember that whenever a electron revolving around the nucleus, or we are going to take whole as the atom, this atom act as a tiny magnet having the magnetic dipole moment this side or opposite to the angular momentum, considering only the orbital angular momentum. Spin, due to spin of electron also we can get the magnetic moment, that we are not going to discuss. We are discussing when the electron revolving around the nucleus, it acts as a magnet having the magnetic moment is mu L, which is opposite to the angular momentum. Some books they are written that is mu M. Some books they are written mu M, and here I written mu L. Okay, so these things you have to be remember. And the mu L value is minus E L vectored by 2m in the vector form, and the magnitude form, this will the magnitude form of the magnetic moment of an electron when it is revolving around the nucleus. Now these things will be required in our discussion of classical Langevin theory of diamagnetism. Okay, so let's start. Actually, diamagnetism is observed in all those substances in which atoms have even number of electrons around the nucleus. Suppose we have an atom and its nucleus is here. Around the nucleus, even number of electrons is present, either 2 electrons or either 4 electrons, like that. So in those type of material we can found the diamagnetism. Actually the diamagnetism are the material we know which are repelling the applied field. Suppose this is the material, and we are going to be apply the magnetic field along this direction. This is our external magnetic field. Inside this specimen or inside this material, the magnetic moments will be induced in this direction. Means the magnetic moments which will be induced inside the material will be the opposite to the applied magnetic field. This is the characteristics of the diamagnetic material, or this phenomenon also called as the diamagnetism. Okay, and this happens if the atoms corresponding this specimen have the even, means even number of electron around the nucleus or in its outermost orbit. Okay. Now, diamagnetism in a material arises due to change in atomic orbital state induced by the applied magnetic field. So here, change in atomic orbital state, that means we can say that suppose this is the nucleus and one electron is revolving. Suppose among these two electrons, suppose we are going to consider first electron orbit. Whenever we have to apply the magnetic field, its orbit's radius, or we can say its angular momentum, angular velocity omega, will be just changed somewhat. From that we can analyze the diamagnetism in the material. That it is written here, diamagnetism in a material arises due to change in atomic orbital states induced by the applied magnetic field. We know that a moving electron is equivalent to a current loop, whatever I discussed in our last class, to a current loop, to a equivalent to a current loop. Here is just current loop. When an external magnetic field is applied, the magnetic flux linked with this current loop tends to change, which alters the current in the loop in such a way as to oppose the change in flux. This change in current is evaluated or confounded by change in frequency of revolution of the electron. Here we have derived mathematically that the magnetic susceptibility will be negative. What I written? See, here I told that suppose this is your nucleus and one electron is revolving around the nucleus. This is nothing but a current loop, and this current loop is nothing but what we discussed in our last class, that it is a tiny magnet having the magnetic dipole moment mu L. So as it is a current loop having the magnetic dipole moment, or we can say this loop is itself a tiny magnet having the magnetic dipole moment, suppose this direction mu L, and it is revolving around this direction. Okay, so whenever we are applying the magnetic field, suppose this direction, what is exactly happening? First we have to consider that this magnetic dipole moment, suppose magnetic dipole moment along this direction in any arbitrary direction, and path is like this. Wait, I am going to draw another figure for you. See, suppose this is our current loop. Initially in the specimen, this is your magnetic material. Suppose one atom we are going to consider. This is the nucleus, this is the electron, and this electron is revolving. Its magnetic dipole moment in this direction, it is revolving. Magnetic dipole moment will be orbital magnetic dipole moment. Okay, orbital magnetic dipole moment in this direction. Suppose we are going to apply magnetic field. What will happen? This tiny loop or tiny magnetic dipole, that means, or we can say this is a magnet. This magnet will be opposed the applied magnetic field. That means its magnetic dipole moment direction will be which direction? This direction. When we are going to apply the magnetic field like this, then this dipole moment will be tends to orient towards the opposite. Means suppose initially it will be this side. When we have to apply the magnetic field from the outside, this orient, or this will be rotates, or it is going to be oppose the applied magnetic field. That means this dipole moment is going to be orient in this direction. is going to be changed from this to this, means trying to opposing the applied magnetic field. This is the characteristics of the diamagnetic material, and this phenomenon is called as the diamagnetism. This what I explained, that things here it has been written that, see, we know that the moving electron is equivalent to current loop. This is the current loop, right? Now when an external magnetic field is applied, B is applied, the magnetic flux linked with this current loop tends to change, with which alters the current in loop. So when the magnetic field is going to be applied, the flux when it is interacting with this loop, what is going to happen? The current of the loop is going to be changed. The current of the loop will be changed, means by changing the velocity. Suppose we can say that this is the electron, one electron is moving this way. The current will be in this direction. If the speed, if the velocity is changed, initially it was v1, suppose it was changed to v2, then obviously current is going to be changed, right? So here we can assume that whenever we are going to apply the magnetic field, its velocity, in which velocity or which angular velocity is revolving around the nucleus, that angular velocity is going to be changed in such a way that initially it was in this direction, and when with applied magnetic field it is going to be orient in this direction with changing its current whatever it was initially. Same thing it has been written. The magnetic flux linked with this current loop tends to change, which alters the current, which alters the current in loop in such a way as to oppose the change in flux. Change in flux means applied magnetic field. In such a way that the current is going to be changed, it is oppose the applied magnetic field, or the so-called change in magnetic flux. Change in flux. This change in current is to evaluated, confirmed by the change in frequency. So I told that if current is changing, means what? The velocity is changing. So here, if the current in the loop is changing, that means the velocity of the electron, here this is suppose the tangential velocity. Okay, tangential velocity is going to be changed. If tangential velocity is going to be changed, its angular velocity also will be going to change. So current is going to be changed when applied magnetic field. That means its angular velocity is going to be changed. If angular velocity is going to change, this is angular velocity, so obviously its angular frequency is going to be changed. So those things it has been written. This change in current is to be evaluated or confirmed by change in frequency of revolution, or the so-called angular frequency of the electron. Here we have derived mathematically that the magnetic susceptibility Xi m will be negative. So these are the characteristics, or how the diamagnetism occurs or developing inside the material. This is the explanations, and we know that the susceptibility of a diamagnetic material is negative because its induced magnetization inside the material is opposing the applied magnetic field. So when the induced magnetization inside the specimen opposing the magnetic field, applied magnetic field, then that specimen is called as the diamagnetic material, and its susceptibility will be negative. So here in our discussion, mathematically we are going to be derive in this lecture, we are going to be derive mathematically the susceptibility will be negative. Okay, so let's start the derivation of the mathematical part of this lecture. So put a heading on your note that mathematical derivation. Okay. For mathematical derivation, let consider an atom having 2 electrons around the nucleus. These 2 electrons move around the nucleus with same speed on like orbits on like orbits means same orbit, on like means similar orbit, but in opposite directions as shown in figure 1. So first we have to consider the one atom. This is its nucleus and two electron. Atom having the 2 electrons, one is revolving anti-clockwise and another is revolving around the nucleus clockwise in the same orbit, on like orbits but opposite in direction. This is the situation, and here the tangential velocity is v, that is the with the same velocity, it is written with the same speed. So at instantaneous velocity is same for this electron and this electron. This is also electron. You just reduce its size. Actually the electron size should have to be less than the nucleus. Here somewhat. Okay. Here correct. So the 2 electrons revolving, this is revolving anti-clockwise, this is clockwise with the same speed. Obviously its angular velocity also will be same, and the so-called angular momentum for this electron will be this side, and magnetic moment will be this side, and for this electron angular momentum direction will be this side and magnetic moment direction will be this side. So this is the situation whatever we have been considered, that the atom have 2 electrons. What I told that the dimagnetism observed only in the even number of electrons around the nucleus. So hence we are considered one nucleus and 2 electrons are present. So one is revolving this side and another is revolving around clockwise. Now what is going to be found mathematically? See, the orbital magnetic moment of one electron equal and opposite to the orbital magnetic moment of the second electron. Suppose this is your first electron, orbital magnetic moment will be this side, for the second it will be this side. Both are equal magnitude and opposite direction. Okay, hence total magnetic moment of the atom, as magnetic moment is a vector, so if the 2 vectors are equal and opposite with the direction which is inside one atom, then what will the total magnetic moment for that atom will be 0. Hence total magnetic moment of a atom, of this atom is 0. That means dimagnetic substance has 0 magnetic moment initially. Initial means without magnetic field applied. So that means dimagnetic substance has 0 magnetic moment in absence of applied magnetic field. In absence of applied magnetic field, we can found the dimagnetic substance has 0 magnetic moment. Okay, now we have to go for the next page of our note. See, here I written the page numbers. Carefully you have to watch. This is the page number 1. Now we have to go for the second page. Let I is the current in the loop. In the first page we consider the 2 loops. For the first electron, this is the loop. Same loop, same orbit, but it is revolving this side anti-clockwise, clockwise. So suppose any one of the loop we have to consider. Let I is the current in the loop, r is the radius of the orbit. Then the magnetic dipole moment of each electron is given as Ia. We know that the magnetic dipole moment will be nothing but I into area of that loop, I into A. So here I into area will be pi r square, right? And I, current, will be nothing but charge by time period, E by T, pi square. The T, the time period, will be nothing but 2 pi by omega 0. Here omega 0 is the angular velocity of the electron, in which the electron is revolving around the nucleus. That means with which frequency the electron is revolving around the nucleus. That is your angular velocity omega 0. This is written as omega 0. This is also omega 0. This omega 0 is vectorially represented in this way. This is vectorially represented in this way, clockwise, anti-clockwise. Okay, this is omega 0. Okay, omega 0. Now see, so T, time period, we know that 2 pi by omega 0. Now we have to put this time period over here, then we can find E by 2 pi by omega 0 into pi r square. Then what we are going to get? See, pi got cancelled, omega 0 is gone to the numerator, and we can get half E omega 0 r square. Let it is equation number 1. Now if we are going to consider this one is the magnetic dipole moment of the first electron, then the second electron, for the second electron it will be opposite, then that is nothing more, we can get the minus of half E omega 0 r square for the second electron. So no need to derive for the second electron, therefore directly we can write, therefore the net magnetic moment of an atom, of the atom, will be mu m is equal to, this is the net magnetic moment, will be equal to half E omega 0 r square minus half E omega 0 r square equal to 0. This is equation number 2. That means this is the net magnetic moment of an atom. Atom means 2 electron we are going to be consider. For the first electron, if it is positive half E omega 0 r square, for the second electron it will be minus half E omega 0 r square. So the net will be 0. So hence net magnetic dipole moment we found for an atom in the absence of any external magnetic field is 0. Okay, now in the absence of external magnetic field, the centripetal force required by the electron is provided by electrostatic force of attraction between the nucleus and electron. See, when the electron is revolving around the nucleus will be here, and here either we are going to be consider the so-called anti-clockwise rotation and clockwise rotation, but both electrons are revolving circular way. Okay, circular way means there will be a will be present a centripetal force, due to which the electron is revolving around the circular motion. So circular motion, wherever we can found the centripetal force, and the centripetal force will be towards the nucleus, right? This centripetal force is produced by the electrostatic force of attraction between the nucleus and electron. So nucleus and electron, suppose here is the electron and this is the nucleus, the centripetal force magnitude is due to, or the centripetal force evolves due to the attraction between the nucleus and the electron, for first electron and for the second electron also. Suppose this electron is revolving this way, also the centripetal force is nothing but due to the electrostatic force of attraction between the nucleus and the electron. Okay, here you can also consider this electron. Okay, so the centripetal force acts on the electron, that may be revolving clockwise, that may be revolving anti-clockwise. That centripetal force evolves due to the attraction between the electron and electrostatic force of attraction between nucleus and electron, and that force is represented by Fc. Force C is nothing but the centripetal force. Okay, Fc will be equal to mv square by r, or we can write m omega 0 square r, because we know that v equal to r omega 0. Let it is equation number 3. And the direction of the centripetal force is towards the center of the orbit, which is shown in the figure 2. Either it is clockwise and anti-clockwise. Next we have to go for the next page. Okay. So in the page 3, we have to consider a apply of magnetic field. Means let us apply an external magnetic field, that is B equal to mu 0 H, on this situation. Here this is the situation of two electrons revolving around the nucleus, but without magnetic field. Now we have to apply the magnetic field. What will be happen, that we are going to be discuss. So here you can see in the figure A, magnetic field is applied to this side parallel and perpendicular to this loop, and also for the electron 2. Consider this is electron 1 and this is electron 2, and this is your nucleus and this is your nucleus. Okay, so whenever we are going to apply magnetic field towards this side, then what is going to be happen on its angular momentum and velocity. So here now let us apply an external magnetic field such that this magnetic field, this field is perpendicular to the plane of orbit. This is your plane of orbit, and we are applying the magnetic field perpendicularly. Okay, this dotted line is shown the magnetic field, applied magnetic field, right? Now when the external magnetic field is applied, when an external magnetic field is applied, then additional force, that is FB, force due to the magnetic field on the charge particle, or the so-called Lorentz force, equal to the magnitude I am telling, equal to EVB, acts on the electron. In our plus 2 we have been studied that if suppose this is your magnetic field, this is your magnetic field, and if a charge particle Q is enters inside the magnetic field with the velocity v, then force on the magnetic field will be Q into V cross B. As V and velocity direction and magnetic field direction both are perpendicular with each other, so it can be written as QVB. So here charge we have been taken as electron, so EVB. V is the velocity of the electron, B is the applied magnetic field. So the extra one magnetic force is going to be induced on the electron when we are going to apply the magnetic field. Initially it was not there. Initially, whenever we are going to consider this situation, only we can get the centripetal force, which is due to electrostatic force of attraction between the nucleus and electron. But when we are going to apply the magnetic field on this situation, a magnetic force is going to be induced. A magnetic force is going to be induced, and whose value will be EVB. In which direction, that we are going to be find out. See, this is the force direction, that is V cross B. See, suppose this is your B direction and this is your V direction. We know applying the left hand thumb rule. Left hand thumb rule means this first finger represents your magnetic field. This is your magnetic field. This is your magnetic field. Okay, and this is your motion of the charge, and this will be show you the force, this will be the so is the force. Okay. If we are going to consider this situation, the magnetic field is this side and the velocity of the charge particle is this side, the force will be this side. That means when this charge particle enters the magnetic field, force will be act towards this side. So due to which this charge particle is going to be revolved inside this magnetic field, that we have already studied here in our +2 level. And the same left hand thumb rule here we are going to be apply. See, this is our velocity direction. This is our velocity direction. Velocity direction is this one. Okay. So you just imagine that your magnetic field is perpendicular to the plane of paper. This B is this direction, okay, and the velocity is along this direction, this direction, okay. Now if magnetic field along this direction and velocity is along this direction, this is your magnetic field direction, this is your velocity of charge particle, then the force will be act on the charge particle towards this direction, that is so called magnetic force. So the magnetic force will be act on this charge particle when the magnetic field is going to be applied perpendicular to this plane. So on this plane the electron is revolving. We are going to be apply the magnetic field along this side because we are going to be apply the field perpendicular to the plane. So this side, and the velocity direction is along this side. So V cross B also, if we are going to apply cross screw rule also it is giving this direction, V cross B along this side, or you can apply the left hand thumb rule, that is magnetic field is this direction, okay, is your velocity this direction, the force will be induced on the charge particle will be this direction, okay. So for this case it will be this direction, magnetic field this direction, velocity will be this direction, and force will be this direction. Magnetic field will be this direction, velocity will be this direction. So we can say that V cross B, see screw rule if we are going to apply, V cross B along this side, or left hand thumb rule also, it is giving this direction. So the magnetic force which will be induced on this electron in the magnetic field towards this direction, on this electron it will be this direction, right? So now as both magnetic force direction is opposite, means for this electron it is this direction, for this electron it will this direction, then obviously the angular velocity for this electron and this electron will be different. So same thing it has been written in this page, you just watch it. I am going to be read. When an external field is applied, then an additional force, that is FB, that is also so called the Lorentz force, equal to EVB, magnitude is how much, EVB, acts on it. It means electron. The direction of the Lorentz force depends on the clockwise and anti-clockwise rotation of the electron. Clockwise means the velocity direction, it is anti-clockwise, velocity direction of the electron is this side, clockwise means velocity direction is this side. So the force on this two electron, the magnetic force on this two electron depends upon its direction of motion, clockwise or anti-clockwise. Now if the FB and FB, for this electron is this side, for this electron is this side, obviously the velocity V1 for electron 1 and for electron 2, the velocity V2 will be both are different. okay, because on this electron the net centripetal force, and on this electron the net centripetal force will be different, because here the centripetal force will be decrease, here the centripetal force is going to be increase. If the centripetal force increased, obviously its omega, here centripetal force decreased and here centripetal force increased, means centripetal force, both the centripetal force are different, obviously its angular velocities will be different and the corresponding linear velocity will be different. So for that, let v1, v2, omega 1, omega 2 are the new linear and angular velocities of the electrons as shown in figure 3. This is your figure 3. Carefully you have to draw the figure. Okay, pause the video and draw the figure. Here I am going to zoom for you that figure, it will be easy for you. See, this is the figure. This side is Fc, this is Fc, it is written Fc, that means centripetal force. The induced magnetic force along this side, Fb. This is your v1, velocity of electron 1, and omega 1, angular velocity of electron 1 when the field, magnetic field is applied. Okay, this is for electron 2, and this is the figure A and B, figure 3. This is your figure 3, and v2 along this side, and Fc this side, Fb also along this side, and this is your omega 2 along clockwise. This is written omega 2, and this is your applied magnetic field. N means nucleus. Okay, and the figure title, it is written that change of linear and angular velocities in magnetic field. Change of linear and angular velocities in magnetic field. Okay, draw this figure by pause the video over here and draw the figure perfectly. Now we have to move forward. Now the centripetal force will be calculated as centripetal force in the absence of magnetic field plus or minus Lorentz force, that is your induced magnetic force. So for electron 1, the centripetal force will be Fc minus E v1b. You got my point. Whenever we are going to apply the magnetic field, this Fb is going to be induced. The magnetic force or the Lorentz force is going to be induced. This Fb will be nothing but EVV. For electron 1, it will be EV1b, and as this one is opposite to the centripetal force, the net centripetal force will be how much? Fc minus Fb. So Fc minus Fb magnitude will be how much? EV1b for the first electron. Okay, so for the first electron we can write m omega 1 square. This is your centripetal force expression, is equal to Fc minus EV1b. Let it is equation number 4, and it is represented in figure 3a. This is your figure 3a. Okay, from the figure 3b, what we can found? We can found that m omega 2 square r will be equal to Fc plus EV2b, because the induced magnetic force will be in the same direction of your centripetal force. So hence both are is going to be add up. So Fc plus EV2b is equal to m omega 2 square r. Here omega 1 is the new angular velocity of electron 1, omega 2 will be the new angular velocity of electron 2. Let it is equation number 4 and 5, and this is represented in figure 3b. figure 3b. Okay, next we have to move for the next page. Now from equation number 4, this is your equation number 4, m omega 1 square r is equal to fc minus e v1b. So from equation number 4, this is written as 4, we get m omega 1 square r equal to fc minus e v1b. That implies m omega 1 square r is equal to, initially fc was how much? It was m omega 0 square r. From the beginning I have been written the initially. Here you can see the fc without any applied magnetic field, the fc, the centripetal force, is m omega 0 square r. So the initial fc is m omega 0 square r minus, here e, v1 can be written as omega 1 into r into b. So r got cancelled in both the side. Then we can found m omega 1 square is equal to m omega 0 square minus e omega 1b. That implies omega 1 square will be equal to omega 0 square minus e omega 1b by m. Let it is equation number 6. Similarly, from equation number 5, that is m omega 2 square r, this is your equation number 5, m omega 2 square r is equal to fc plus e v to b, right? From equation number 5, that is m omega 2 square r is equal to fc plus e v to b, we can found omega 2 square. Similarly, fc is nothing but omega 0 square r. Here v2 will be written as r omega 2 b, and we can found omega 2 square will be equal to omega 0 square plus e omega 2 b by m. Let it is equation number 7. Now we have to subtract 7 from 6. What we are going to get? Omega 1 square minus omega 2 square will be equal to, this is omega 0 square, and omega 0 square is going to be cancelled out. So here we can find minus e omega 1 b by m. This will be also minus e omega 2 b by m. Now take common from both the terms, minus e b by m, we can found omega 1 plus omega 2. Okay, so here this is in the form of a square minus b square. So we can write a minus b into a plus b, omega 1 minus omega 2 into omega 1 plus omega 2 is equal to minus eb by m, omega 1 plus omega 2. So this and this got cancelled, and we found omega 1 minus omega 2 is equal to minus eb by m, or we can write del omega is equal to minus e b by m. Let it is equation number 8. Okay, come to the next page. So, but it is well known that if angular velocity of electron omega, then the magnetic moment of electron will be half e omega r square. So what it is telling, that magnetic moment of an electron will be this expression, because from the beginning, this is from equation number 1. That means from, I am telling that from beginning we discussed that the so-called magnetic dipole moment of an electron is nothing but, that is half e omega 0 square r square. So here E is the charge of the electron, r is the radius of the circular orbit, omega 0 is nothing but the angular velocity. Suppose we are going to consider the omega, instead of omega 0 we are going to consider omega is the angular velocity. So obviously the magnetic dipole moment of the electron will be half e omega r square. Okay, the same thing it has been written, but it is well known that if angular velocity of electron is omega, then magnetic moment of electron will be, it will be written as mu m equal to half e omega r square. From equation number 1, we taken the help of equation number 1 and written this one. Let this is equation number 9. Now the change in magnetic moment due to the change in omega will be how much? So here the omega is the angular velocity of the electron. Okay, now change in magnetic moment, that means del mu m, this is a subscript, okay, mu m, like that it is written, subscript of mu, this is m, don't write mu m, it is this is wrong, okay, this is correct. So del mu m, the change in magnetic moment will happens due to change in omega. So it can be written as del mu m will be equal to half E del omega r square, right? So del omega we found in our equation number 8, del omega, this is the relative change of this is the relative change of angular velocity of 2 electrons of an atom. Here you just write, so you just write that this is the relative change of angular velocity of 2 electrons, this d omega, this is the omega 1 after changed, the omega, this is the omega 1 after applying the magnetic field for the electron 1, this is the angular velocity of electron 2 after applying the magnetic field, okay, after applying the magnetic field, this is omega 1 and this is omega 2. The relative change of angular velocity from 1 to 2 will be nothing but the so called omega 1 minus omega 2, or del omega is nothing but minus EB by m. Now we are going to put this value here. The change in magnetic moment due to the change in omega will be this much, and instead of del omega we can put minus EB by m, whatever we found in equation number 8. Equation number 8, minus EB by m. So here also I written from equation number 8. So del mu m will be equal to minus b e square r square by 2m, let it is equation number 10. Okay. Now here this expression is nothing but change is actually the relative change in somewhat wait. So this expression, what it is telling, that is means this is the change of magnetic moment, but this change, that means this change is actually the relative change in dipole moment of 2 electrons, because here we consider del omega is nothing but relative change of 2 electrons. Here this is nothing but relative change of angular velocity of 2 electrons. So hence this expression will be what? This expression will be change. This change is actually the relative change in dipole moment of 2 electrons due to change in their angular velocity. Angular velocities, change angular velocities, right? Now we are going to consider change of dipole moment individual electron. This is the change of dipole moment between one electron to another. Now we are going to consider change of dipole moment for each and every electron or individual electron. That will be how much? So here we have to stop our discussion today, and in the next class we have to discuss from here. Okay, today we have to stop over here, and in the next class we are going to discuss about the change in dipole moment of the each electron. Okay, so up to this much, you carefully watch this video, write down the note perfectly, and if in doubt you can ask me, we have to discuss. So thank you so much for watching this video. In next class we have to discuss this one up to end of this topic. Okay, thank you so much. Thank you.